Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us. My name's Andrew Dunkley, and with me, of course, is astronomer at large Fred Watson for episode 125 of Space Nuts. Hello, Fred.
We are churning through them, Andrew, aren't we? They seem to come and go with incredible regularity.
Absolutely.
I'm worried we're in a sort of one of these time warps that doesn't let us move.
Yeah, like a Groundhog Day scenario.
Groundhog Day. That was what I was yeah.
Yes, I get that feeling sometimes. My Monday to Fridays are nothing like they used to be, and there's all sorts of quirks and bends in the road in my normal week, so there's nothing normal about my life anymore.
No, that's good. It keeps you young.
It does.
But just to reassure our listeners, we do cover new stuff every week.
Yes. If you think we've spoken about something before, then it's your imagination, or we have.
It almost certainly will have had. And
yes.
in fact, our first story today is exactly like that, because we've talked about this before, but we're going to talk about it again.
Yes, this is an interesting story about fast radio bursts that have been detected. I think they're saying they've found about 20 of them, which is very exciting. We're also going to look at geomagnetic thunder. Geomagnetic storms are well known, and of course the northern and southern lights and all that sort of stuff, but apparently they do make noise. And we've got a couple of questions we're going to bump off today. Our good friend Aziz in Uganda has sent us a question which I initially thought had nothing to do with astronomy, but Fred tells me there is a link. And we've got another question about particles at absolute zero, whether or not we can detect them with current technology. We will find out, because Fred knows. Fred knows everything. But first, Fred, let's talk about these fast radio bursts that have been detected. Now, I am automatically defaulting my brain to the WOW signal, which was a big radio burst that they detected once and never again, and they've been looking for it ever since. Is this the same kind of thing?
I think this is different, because the WOW signal was lasted for a considerable time. I think it was something like 79 seconds, and that 79 seconds was while whatever was emitting the signal was in the beam of the telescope, because this is a radio telescope. So it probably lasted longer, but they never found it again, as you said. So these are quite different. And a colleague I was speaking with last night said that they should be called fast radio bursts. It's because they're fast.
So rather than fast radio bursts, they're fast radio bursts.
That's right, fast radio bursts.
Okay. That's pretty good astronomical humour.
I think so too.
Got to give him a big tick for that one.
Yeah, you do. Sadly, he wasn't an astronomer; he was a radio announcer.
Yes.
That's why.
Yes.
Anyway, so what are fast radio bursts? They are things that were detected actually back in, I think it was 2007, when a group of American astronomers who were interested in supernovae, which are exploding stars, they were trawling through the data from the Parkes Radio Telescope, because that's all archived, and you can go back and look through it if you're a scientist and make head and tail of what it means. But that's what they were doing, and they came across this signal, the fast radio burst, which was exactly as the name described, because that's what they've been called. It lasts for a millisecond. So 1,000th of a second.
Wow, that is fast.
It's very fast, yeah, and pours out a colossal amount of energy in that time. And so that was the first one. Since then, over the years, that's 11 years ago, 34 of these things have been detected. And two things about them. One is that they are all over the sky. They're not in a particular direction. So they're not some alien species signaling from one corner of the universe.
Well, in that sort of time, you can't even say hello. You go,
that's right.
That's about it.
Yeah,
what was that again? We're invading is what they're saying. No.
Yeah, so it's not. So it is some natural phenomenon. The other thing is that one of these fast radio bursts, or these sources, whatever they are, actually repeats, and I think it's repeated, a dozen times or something like that. So this is in exactly the same direction, but that is the only one that does. Most of them are just one-offs, and they kind of come and go. There was a bit of and I'm sure you and I have talked about this. There was a little bit of a furphy, a false alarm, a red herring is what the words I'm looking for, which happened a few years ago when there was a signal that was very similar to fast radio bursts, but was eventually traced to people opening the microwave cooker door in the Parkes radio telescope.
That's right.
Or they switched it off.
I remember.
So as you open it, there's this fast radio burst comes out, which the telescope picks up. They even gave them a name, peritons they called them, but they are now known to be, terrestrial in source, in origin.
That made big news in Australia.
Yeah, it did. I know.
That was huge.
Yeah.
That's a slow news day story for sure.
It's terribly embarrassing though, when you.
It's not as embarrassing as saying that the universe is brown when it's actually blue.
Oh well, we did that too. Yeah, no, it's the other way around.
Was it?
The first it was turquoise at first, and to be honest, I have to say I looked at that paper and I know the guy who did it, and he's pretty smart, and I thought that can't be right. The universe cannot be turquoise. It's the wrong colour. And then about a week later, he released another bulletin that said, no, I got it wrong. It's, what was it, beige, I think it was.
Beige, yeah. Pretty boring when you think about it.
Anyway, notwithstanding all that, the reason why we're talking about fast radio bursts again is that the Australian Square Kilometre Array Pathfinder, or ASCAP, this is a telescope which is in Murchison in Western Australia. It's in the desert, although when I visited it last month, it poured down. It was very, very wet. It's actually quite pretty country with a lot of scrubland. It's very flat. And interesting plants too at this time of the year, especially when there's a bit of rain, including something called Sturt's Desert Pea, which I've never seen before.
That's a lovely plant.
Very spectacular. Anyway, yes, so the ASCAP telescope has just come online basically over the last decade. It's 36 radio antennas spread over an area of the Murchison Desert, and they're linked together as these radio telescopes are. But these are quite special because they've got, instead of just a single radio feed imagine what they're like. It's a dish antenna, basically like a paraboloid, just like the Parkes dish, only not quite as big. They're about 12 meters. And then what you expect is, all right, that those radio waves are collected and beamed into what in the trade is called a feed horn. It's where the radio signal disappears into a waveguide, and then you do all your work on it after that. But these things don't work like that, because that means you can only look in one direction in space. The ASCAP telescopes have got something which you could call, I guess, an image sensor, but a radio image sensor. So exactly like your mobile phone or your camera, which has a silicon image sensor in to sense the light and build up the picture. This thing, it's called a PAF, which means phased array feed. That is basically an image sensor. It's fairly crude. It's not fine detail, but it's good enough that you can, with one of these antennas, you can look at an area of sky 100 times the size of the full moon, the area of the full moon.
Not bad.
But they've done something even more clever in this search for fast radio bursts. They've used all the antennas individually. They've linked them together, but they've had them all pointing in just slightly different directions. So you get a fly's eye effect, and you can look at 1,000 times the area of the full moon. And sure enough, they've netted a world record number of these fast radio bursts, 20 more in the last year.
So in other words, they've found a way of finding them.
They found a way of finding them, that's right. And what we hope is coming next, and I was talking to one of my colleagues a week or so ago who's involved with this work, is to be able to identify which galaxy these things are coming from, because we do know that they come from a long way away. And what tells us that is something called dispersion. As the radio waves travel through space, the high-frequency waves get slightly ahead of the low-frequency waves, and that's because they interact with electrons in deep space. And what that does is it slows down the low-frequency signal, and so you get the high-frequency arrives first. It's just a very short time, so, still thousandths of a second, but there is enough of a difference between the high frequency and the low frequency that you know that these things have come a very long way. They've come through space, through intergalactic space. So we're talking about billions of light years away. Hopefully, very soon we'll be able to point to a galaxy and say, this is where the fast radio burst is coming from, and maybe even follow up with with optical telescopes when they happen, visible light telescopes, to see if there's a flash or something like that.
Yeah, fascinating. And
I think it is too. It's a big mystery. We don't know what they are. They're probably
I imagine they'll decipher the message, and it'll be a long time ago in a galaxy far, far away.
There was a fast radio burst.
That's right. Yeah. Oh, it's very exciting. Because one more mystery solved, we hope.
Well, it will be nice to solve it. That's right.
Indeed.
It's one of the big mysteries. But it's good to have mysteries as well.
All right. We'll probably hear more about that down the track. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by TechRadar. This is the one I use. I've been using it for a couple of years, and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons, and there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Now, Fred, to something unusual and yet fascinating, and that is auroras. We have auroras in the northern and southern hemisphere at various times, but certainly much more spectacular up north. Let me qualify. More people see them up north than down south because of the way the population's spread around the world. But they are fascinating. They are truly fascinating. And you've actually gone on expeditions to look at these things in the past.
That's correct. Yes, I've taken, I think, 5 expeditions up to far northern Scandinavia, and occasionally to Iceland as well. We've been to Iceland, and so. Being underneath an auroral display is just staggering. It's the whole sky's lit up with these green and sometimes magenta colours. Really,
and occasionally beige.
Occasionally beige. That's right. Yeah, look, you do. You get a mixture of colours, and we now understand pretty well what causes this. These are subatomic particles from the sun, electrons and protons being funneled by the Earth's magnetic field to interact with the atoms of the Earth's atmosphere, and that's what causes the colours. It's the Earth's atmosphere being excited to display these colours. The path of the electrons is a curious one, though, because they go past the Earth and then fall back and come back in from the other side, the side away from the sun. It's a very complicated process, but well studied, and there are. Particularly in northern Scandinavia, there are several institutions which exist to basically map out the upper atmosphere and work out what's happening there, many of which I've visited. But one of the other things about the aurora, the northern lights, and we are talking now about the northern lights, although the southern lights are symmetrical, so it would be the same. But as you say, there's nobody there to see them.
That's right.
One of the things that has impressed me, I've talked to physicists and lots of people who work on this up in northern Scandinavia, but also when you talk to, the locals, and particularly the Sami people, the indigenous people of that area, the Laplanders, basically, there's a common theme that says you can hear the aurora, that they do make sounds.
Now, that comes as quite a surprise to me, because I thought that you would stand under these things and you would see them, but it would be in total silence. Has that been your experience?
It has indeed. That's been my experience. No sounds at all. And scientists for a long time have been very, very skeptical about this. You don't hear things. It must have been the snow crackling or something like that. But now we've got really hard scientific evidence that there are noises. And it's actually some work that's been done in Aalto University, which is in Finland. And there's a team there that are using whole sets of microphones to record any sounds that might turn up during an auroral display. And sure enough, they get them, they pick them up. And it's slightly more, it's more technical than that, because since they're using many microphones set out in an array, they can triangulate. So when they hear noises, they can work out exactly where these noises are coming from. And it seems to be that they typically come from what's called an inversion layer. This is a layer of the atmosphere where the temperature changes rapidly. So it's probably colder near the ground and then slightly warmer above. And at about 70 meters above the ground, that is where these auroral sounds seem to come from. And they're speculating that the inversion layer causes the charged particles in the air to be separated and then come back together again with a little clap, because the pressure's changing.
I'm totally surprised that an aurora, which is way up there,
90 kilometers is
would
the low,
have an effect on something 70 meters above the ground.
Yeah, so it's all about. I guess it's more to do with the particles that make it to the ground or make it much nearer the ground, but that don't see. That you don't see. They've lost the energy that you require to excite the atmosphere. But it clearly is linking the sounds to the brightest aurorae. They apparently the sounds come when the aurorae are brightest. They've done what you call a spectral analysis. They've worked out what frequencies these sounds are, and they're right in the middle of the audio spectrum, so people can hear them. So
if you're in the right place at the right time, under the right conditions, you will hear an aurora.
That is right, probably.
Okay. So, and the sound is more like a snap, you said?
Well, yes, apparently there's a range of sounds, but one of the ones that we've got recorded that you might be able to play, Andrew,
I'm going to try.
It sounds just like a pair of clapping sticks coming together, the wooden clapping sticks.
So this is what they sound like, if we can get this right. Yeah. It just sounds like someone warming up in a recording studio. Hang on, let's try that again.
Yeah.
So that's what it sounds like.
So it is. There's definitely there's a definite click there. So the scientist who's doing this work, whose name is Unto Lane, says people who talk and walk around concentrating on picture taking might never hear a single sound related to an aurora. You've got to stop all other activities and focus on listening. We Finns are probably good at this because we've received more than 300 reports of sound observations during their auroral acoustics project. And he says he's learned that a geomagnetic storm by itself isn't enough to produce them. You also require a strong inversion layer, which acts like an electrostatic loudspeaker. Without it, there are no sounds. And that explains why a lot of these geomagnetic storms are silent. He says it's like geomagnetic thunder, which is a very nice way of putting it.
Yeah, fascinating. Oh, wow. Yeah, and thanks to spaceweather.com, because that's where we picked the sound up. Yeah, let's have another listen to it. There it is.
Yeah, great.
Awesome.
Definitely.
So next time, those of you who are close enough to the Northern Hemisphere areas that pick up the aurora, just shut up for a while. Have a listen.
And stop going, wow, oh, look at that,
yeah.
wow.
Well, you can't help it, can you?
No,
really?
you can't. Absolutely can't.
They're quite amazing. You're listening to Space Nuts. Andrew Dunkley here and Fred Watson there.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Finally, Fred, we're going to tackle a couple of questions today, mainly because they're really simple, or maybe not. Firstly, Aziz in Uganda, who's actually sent us a question before, wants to know if we can explain what causes ball lightning. Is it luminous plasma? Now, I initially thought, well, this is not an astronomical question, but you said there is a connection.
There is a connection, that's right. So, ball lightnings, it's a bit like the story we've just done about the aurora. It's one of these things that people have reported over many years. There are clearly enough reports to know that ball lightning is a real phenomenon.
Yes, and I've heard stories of it sort of going through walls and floating around in rooms and through passenger aircraft, all sorts of stories.
That's right, yeah. So that seems to be what it is. It's during a thunderstorm, during electrical activity in the atmosphere, you sometimes get this plasma that comes together and becomes luminous. And seems to be sustaining. It lasts for quite a long time. Now, I've never seen it. I would love to see it.
Oh, me too.
But so it's not well understood. However, about probably 2 years ago now, a colleague of mine, actually in the Queensland University of Technology, who is really an interesting guy. He's a very good scientist. His first name is Steve, and I'm desperately trying to remember his second name, which is terribly embarrassing. If you're listening to this, Steve, I'm sorry, on the spur of the moment. It'll come to me probably by the end of the story. But he has investigated ball lightning, and there was a report of ball lightning in Queensland. Actually, it's probably more than a couple of years ago. This might be 5 years ago, something of that sort. Steve Hughes, his name is, by the way. I knew I'd get it. And he realised that when the reports of this ball lightning were coming in, it was at the same time as a fireball had been seen in the upper atmosphere. So a fireball is quite different. A fireball's a meteor, a bright meteor that slashes through the upper atmosphere and burns up. But unlike a meteor, which just looks like a shooting star, it's a great name for them because that's exactly what it looks like. A fireball is much brighter because it's a bigger chunk of stuff. It's probably the size of a football or something like that. And it hits the atmosphere at 30 or 40 or whatever kilometers per second and burns up. And a fireball can light up the entire landscape. They're quite dramatic. I've seen several fireballs. But Stephen was able to link the fireball with the ball lightning. And the suggestion is that there is some kind of transfer mechanism between the upper atmosphere and the ground. And it's like your question about the aurora, how aurora take place above 90 kilometers. How can that affect things going on at the inversion layer on the ground. And the same will be true with the fireball. The fireball hits the atmosphere at about the same height, actually. It's the upper atmosphere, 90 or so kilometers. How can that affect plasmas on the ground? We don't really know, but there are clearly mechanisms that allow that to happen. And I think, as far as I know, Stephen's paper has been, as it was peer-reviewed. It's not one that's just idle speculation. I don't think it has been discredited in any way. So I don't know there might well have been other work done on it since then, which I'd be very interested to hear about. But yeah, it looks as though there is a link with astronomy and ball lightning.
So, Aziz, yes, it is luminous plasma. We don't really know why, but it's connected to fireballs.
Yep, that's right.
Fascinating. I keep saying that word, but we're having a fascinating day.
Well, I think it is.
Yeah. Great question too, Aziz. Thank you. Let's move on to a question now from John Brooks from Callala Bay in New South Wales, which sounds like a rather nice part of the world. If there is a particle or object at absolute zero, can we detect it with our current technology, or is it invisible like dark matter?
Paradoxically, it doesn't become invisible. So temperature, as you know, is the result of particles vibrating, basically. And as you cool them down, they vibrate less and less. And so you'd think that when you get to absolute zero, because absolute zero is defined as the temperature below which nothing can exist, you would expect them to stop vibrating altogether and have zero energy. So theoretically, absolute zero is indeed the temperature at which particles are at their lowest energy points. But paradoxically, they don't lose all their energy. And that's because of quantum physics. Yeah, quantum physics means that there is always an uncertainty. And so even at absolute zero, there is something called 0 point energy. So you take away all the energy from the particles that you can remove, but there's still some energy there. And it's because of, so actually it comes about because of the uncertainty principle. I've talked about Heisenberg's uncertainty principle before, which says that you can know a particle's position or its momentum, but not both to the same accuracy. You can know if you know its position, then there's an uncertainty in its momentum. And if you know its momentum, that's basically its speed and its mass. You don't know where it is. Its position's uncertain, and that's at the basis of quantum physics. So the same applies to absolute zero. You've still got an energy. So if you know where a particle is, you don't know anything about its energy. And that's why you can get to absolute zero. Don't shake your head.
I'm
easy to understand.
I'm shaking out the fog. It's very confusing. But you
can't. So the bottom line is you cannot stop a particle completely, because if you did that, then you would know both its momentum and its position exactly, and you can't know those two. So you can't stop the particle vibrating. So it still has some energy, even when it's at absolute zero.
Gotcha. All right. Of course, we are scientists and technicians around the world are trying to perfect quantum computing, and they're on the cusp of making some mileage in that regard. If we start to sort of get our heads around this stuff, it's going to make a huge difference to the world, because these things will be able to work at incredibly fast rates compared to current technology.
Very much so, that's right.
And some of the world's problems will be solved much faster with quantum technology. So, getting our heads around this is getting ever closer. Not mine personally, but in general, we are. I think they've already made prototypes of quantum computers, I believe.
Yeah, here in Australia, there are some leading scientists working on this. One of whom I'll meet tomorrow night, in fact.
Ah, yes, because you're in Canberra at the moment, or as we Australians like to call the city of the centre of our federal government, Canberra. But so what's happening in Canberra, Fred?
Oh dear. Well, I can't possibly, as a public servant, I can't possibly comment on that. I can't possibly comment. That's why it's called Canberra.
Fair enough. So why are you there? Or is that top secret?
Oh, no, it's not. Tomorrow night is the awards ceremony for the Prime Minister's Science Prizes. And I'll be helping to MC it, in fact.
Lovely.
Yeah, which is we're going to do a double act, which I hope will be a lot of fun. The reason why I mentioned the leading light in quantum computing, though, is Professor Michelle Simmons from UNSW, University of New South Wales. She's not a prize winner, but I happened to see her name on the guest list. She's had many, many awards. And I thought, I wonder if I'll get a chance to talk to her. I bet I don't, but it would be interesting to do that.
Well, you probably got more chance of talking to her than I have of talking to Harry and Meghan tomorrow.
I don't know. I think they'll make a beeline for you, Andrew. They probably listen to Space Nuts.
I dare say they do, and if they do, then I'm in Dubbo. I'll be wearing the orange shirt.
Yeah, good on you.
With a copy of my book tucked under my arm too, I think.
That's right.
And before we go, one more thing, Fred. I would like to send a shout out to David Astle at ABC Radio in Melbourne, who's a big fan of the show, and I know you talk to him regularly. So thanks for liking us, David. It's lovely. And as a former staff member of the ABC, I can't help myself.
Good stuff. And it's great to talk to David, and he's a big fan, which is very nice to hear.
Yes,
I didn't think anybody listened to this,
Oh, look, not even Mandu the cat.
No, well, he's asleep.
Again. Yeah. You sure he's not dead?
No.
He's always asleep when we talk to you these days.
Yeah, he is, yeah.
No, I've heard him sort of rise and fall a couple of times recently. Just not when we're recording. All right, Fred, thank you so much. And thanks to Aziz and John for the questions. We really appreciate it. We do our best to answer as many as possible and keep them coming. We'll do our very best again. And Fred, we'll catch you again in the not too distant future.
I look forward to it, Andrew, and have a good week.
Fred Watson, astronomer in charge. He is one half of Space Nuts, and we'll catch you again next time. Thanks for listening.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.